In our last discussion about waves, gave many examples because the periodic phenomenon known as waves that transfer energy through space, many forms. The waves on the ocean, waves of light were examples that we talked about, and also the vibrations that cause waves to propagate across this room so that you can hear the sound of my voice. Sound is a vibration in the pressure of a medium, which is typically air. When we talk about sound, we most commonly think about sound in the context of what we hear, for example, in this classroom today. But the fact of the matter is that sound travels underwater, and sound actually can also travel through solids. So the concept is really about the vibration of a medium. Sound is a longitudinal wave. When we discussed wave properties in general, I said that there were two types. The longitudinal, which was sort of a push-pull wave, and the transverse wave, which is more of an up and down wave. Transverse waves are like ocean waves. Sound waves are push-pull waves. The vocal cords in my throat push on the air and pull on the air, causing the air to vibrate, and it's those vibrations that travel through space. Now, there's a speed of sound, and I think in everyday conversation, the speed of sound sometimes comes up. But there's a particular speed at which sound waves travel. In our last discussion, we had a wave speed equation, and that applies to all waves, including the sound waves that we're interested in discussing today. But the speed of sound is not one specific number. The speed of sound changes depending on the medium that's being vibrated and the properties of that medium. For example, if you ask me what is the speed of sound of air in this room, I would give a number that's typical for the speed of sound in this kind of atmosphere with this humidity at this temperature, because it's the properties of the air. But speed has an entirely different sound in water or in steel or in very cold air or very dry air, very hot air. So the properties of the medium go into determining what the speed of sound will be as it travels through space. So though we've seen this diagram before, vibrations cause waves. So here I have a tuning fork that pushes and pulls on the air, and I had described this in terms of the compressions, where you can see in the diagram that the air molecules are sort of indicated as being very close together. And the gaps in between where the air molecules are rare, these are actually called rarefactions, which I concede is a very uncommon word. The waviness of the longitudinal sound wave is not up and down, it's compression and rarefaction. Our definition of wavelength is the distance in space from peak to peak. Well, where are the peaks here? In the context of a sound wave, the peak would be the region of maximum compression. So the wavelength of this sound wave would be from the maximum compression, say here, where the molecules are very close together, to the next maximum compression would be the wavelength of the air. In just a bit, I'm going to do a calculation that'll give you a very good idea why we don't typically talk about sound waves in the context of their wavelength, but instead their frequency. But that's how I define the wavelength, and since the wave is traveling through space, there's a timing to that, a periodicity, which is the whole reason why we're talking about it in the first place. Sound waves can exist in any elastic substance. Cast your memory back. Elasticity is all about, or describes the property whereby a thing is displaced or bent or stretched or pushed, and after that it returns to its original shape. The default example we use for that is a spring. If I stretch a spring from its equilibrium length and then release it, it returns to its equilibrium shape. This is an essential property for a medium that carries sound to have, because when the medium is pushed and then the push stops, for example, the tuning fork pushes on the air and then vibrates back again, when the push disappears, the medium springs back to its original shape. The elasticity of the medium is what makes it possible for the medium to vibrate when that vibration is induced by something like a tuning fork. So any elastic substance, and that's why it's not just gases like air, but also liquids and solids or plasma. There's another state of matter called plasma that you may have heard of. They all can transmit sound. Sound waves travel through the earth. Sound waves travel through the atmosphere of the earth. Sound waves don't travel through space because there are no molecules, not many. The density of molecules in space is about 1 particle per cubic meter. The density of space is extraordinarily low. And so there's no medium to oscillate. And so sound waves do not propagate through space the way they sometimes do in science fiction films. It is often true that the denser the material, the faster the waves travel. It's not explicitly always true. Yeah.
How could satellite then, is that like sound going through the air?
Okay, so a baseball hits a pole is a fantastic example. Baseball hits a pole, does that count as a home run? Yeah, if you hit the foul pole, it's a home run, isn't it? So you hit the foul pole, which is good news because it's a home run, and everyone in the stands hears ping. That is not the speed of sound in the pole. The ping that you hear when the baseball hits the pole is the vibration of the surface of the pole pushing on the air, which creates vibrations in the air which travel to your ear. Sound does travel through the pole, but what I mean by that is, if I went to the top of the pole, when the pole was struck by the baseball, say at the low end of the pole, that would create vibrations, and the vibrations in the pole would travel up the pole, and I could detect them at the top. How would I detect them at the top? Well, qualitatively, I could just put my fingers there and I would feel the vibration at the top of the pole. The vibration from the impact of the baseball travels up the pole with a particular speed, and that would be the speed of sound in steel. That's still a sound wave, even if no one's there to hear it. And I had no intention of saying this, but you've heard this. If a tree falls in the woods and no one's there to hear it, does it make a sound? The answer is yes, it does make a sound. Oh no, there's no answer to that. Yes, there is. It does make a sound. The reason why is that sound is the vibrations of air, and those vibrations happen. The reason why there's any argument about it is we don't want to get confused about the sensation of sound, which is what the human brain interprets from the nervous impulses that are created by the vibration of the membranes in your ear. The sensation of sound is not sound. That's a sensation in human, that's a human, I want to say human observation, but it's human sensation. Sound is a vibration. Can a vibration travel up a metal pole? Absolutely it can. And I think even in your life experience, well, as a matter of fact, if you've swung a bat, metal bat, pros use wood bat. You can get a stinger from a wood bat too, but if you're using a metal bat and you catch the ball just right on the bat, the vibrations of that impact go right into your fingers and you can get what's called a stinger. And it is it's like hitting the funny bone. Your brain says nope as soon as it happens because the vibrations travel through the bat into your hands. Sound travels about 4 times faster in water than it does in air. 4 times faster in water than it does in air. And about 15 times faster in steel. So the speed of sound depends on the medium that it's traveling through. And our sensation of sound, by the way, depends on the speed of the waves. Very rare experience, but if you've ever been underwater, like horsing around in a swimming pool and you hear noises underwater, because your ears still work when you're underwater. Instead of sounding the way they do in air, the way your ears have evolved to work, sound underwater is sort of wah, 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 kind of thing. And that's actually due to the properties of the vibrations not being compatible with your eardrums. And the properties of the waves certainly are associated with the wave speeds. The speed of sound in air is about 340 meters per second. I said about because it depends on so many things. The speed of sound in this room is more or less a specific value because of the air pressure, the temperature, the humidity of the air in this room. Anywhere else we go in the world, those values are different. If we go to the beach right now, the humidity and temperature are completely different. If we go to Denver right now, the air pressure is different because of being so high above sea level. The speed of sound in air at room temperature is around 340 meters per second. And if you were engineering something or trying to work out an effect that you observed somewhere around in your experience, you'd use 340 to get it, and you'd get a pretty good value for it. So a quick calculation using my speed equation. Here it is again. The speed of any wave, not just sound waves, light waves, earthquake waves, any kind of wave you can think of, waves on a string, all waves. The speed of waves is the frequency multiplied by the wavelength. Now an A note, which I've referenced before, is 440 hertz. The musical among us are probably thinking to themselves, fool, there's more than one A note. Yes, and we're going to cover that next time when we talk about music. But an A note is about 440 hertz. So to figure out what the wavelength of a sound wave is, I'm just curious. Like I just saw a diagram on the screen that had these compressions and rarefactions drawn out for me, but how big are they actually? Well, I stir the equation around so that the wavelength is equal to the speed of the waves divided by the frequency. That's 340 meters per second divided by the frequency 440 hertz. Now remember, I'm running hertz there, and that's kind of fancy, but that's per second. So I've got a 1 over second in the denominator, which will cancel these seconds here, and this is going to work out to meters, and it works out to 0.77 meters, or that's the wavelength of an A note in this classroom. That's the air being pushed and pulled. You can't see it, but that gives you some visualization that the air in the room is vibrating with compressions and rarefactions on that scale. Notice that the lambda is a small number, a decimal number, which is why we use frequency to describe waves, because it's a larger number. It's just a question of scale. The frequency is a I don't know, an aesthetically more pleasing number to work with. Don't like to work with decimals. Human beings don't like that so much. So it's an aesthetically pleasing number, which is why we use frequency to describe sound waves. There's an effect that I know that you're aware of, and perhaps you've become curious of it. The best example a common example, is police car sirens. But I think slightly more obscure but more telling is a race car. I might tell you a story about how I went to a NASCAR race. It would be a lie, because I would not go to a NASCAR race, but folks are into that sort of thing. And imagine I have very good seats, and I'm telling you the story about how my seats at the NASCAR race were excellent. I'm sitting right down front, and here come the race cars. Wow, that must have been impressive as those race cars went by at high speed. Yeah, I would say, and you wouldn't even believe it. They come around the curve, and here they come. Now that's silly sound effect I made with my face, but that's really what it sounds like, isn't it? As the car approaches, it makes a sound that has a higher pitch. We'll come to understand that that higher pitch means a higher frequency. Now the frequency comes from all of the vibrating parts of the car. Car has not only is the car rotating motion as the pistons drive the transmission around, but that motion causes the vibration of every other damn part of the car, and ultimately the outside of the car is in contact with the air, and that vibration produces sound that has a particular frequency. Whatever that frequency is, I don't know. But then the car passes us, and the frequency drops to a lower value as it goes by. The frequency drops. This effect is called the Doppler effect. And it's also true of sirens. If a police car is approaching, woo, 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 as it goes away, the frequency drops. Not only does it apply to sound waves, but very famously, it applies to light waves as well. When I look through a telescope at the stars in our universe, that light has frequencies. It turns out many frequencies at once, but that doesn't particularly matter to this argument. The light that I look at through a telescope has frequencies, and what we've discovered is that some things that we see through telescopes are more red, and that red color happens to correspond to lower frequencies. And there are some things that we look through our telescopes at that are more blue, and that blue, it will turn out, corresponds to higher frequencies. What's happening is that when I look out into space at all of those things, they're not stationary, they're moving around. The stars that are moving away from me are more red. and the stars that are coming toward me are more blue. There's no issue of stars passing me, but if they did pass me, they would go blue-red as they went by. In astronomy, this is known as the red shift, a change in frequency due to relative motion, and it's called the Doppler shift. Here's a visualization of why this effect happens. Imagine there's some sort of insect, like a cricket, I don't know, and it produces a sound. You're all in front of me listening to the sound of my voice, but if you were behind me, you'd hear me too, because in general, the sounds that I create travel out in all directions. So here is a bug creating some kind of chirping sound that is continuous. Not chirp, don't think chirp, 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 chirp for these concentric circles. Think chirp, a singing cricket, I don't know, Jiminy Cricket. And these lines represent the compressions. And so you can see on the diagram the wavelength. The distance from one circle to the next concentric circle is the wavelength of the sound. So the bug is sitting there happily, making a long chirp, and the sound waves travel away. But if the bug moves, the bug will effectively chase its own sound waves. It'll emit a sound wave, and as that wave travels away, it will chase its own sound wave as it moves away. But of course, it'll be leaving the other one behind. And as a result, it skews the entire wave. Now look, in the direction the bug is traveling, the waves get closer together. And that makes sense because the bug is chasing those sound waves. But on the leaving the waves behind, the wavelength gets larger. Now, since speed is equal to the frequency times the wavelength, when the wavelength gets shorter, the frequency is higher. So if someone were over here listening to this, they would hear a higher frequency of sound because the wave crests are closer together. An observer on this side, listening to these waves that arrive, would hear a frequency that was lower because the waves are further apart. And if you were to pass this, what would it look like? High frequency and then low frequency. It would look like high frequency to low frequency. The Doppler effect due to relative motion. Don't freak out. There's an equation for this, right? The most elaborate equation I think we've seen in all of our physics so far. Particularly because it's got this funny little symbol here in the numerator between V and V naught, which is called plus or minus. Shannon, in the bottom you put it upside down. No, I didn't. In the denominator, it's minus or plus. In the denominator, it's minus or plus. What this equation does is describes F0, or FO, I should say. FO, the frequency the observer will hear, is equal to the frequency that the source emits. So the O and the S are observer and source. If neither the observer or the source is moving, then V observer is 0 and Vs is 0, and so this ratio is 1, and the observer hears the frequency of the source. So if everything stays put, the observer hears the frequency of the source. But if the observer is moving toward the source, if the observer moves toward the source, then the frequency will get higher. So this should be a plus. If the observer moves away from the source, then the frequency will get less. And so this will have to be a minus to make the overall calculation turn out to be less. So I choose my pluses or minuses depending on the relative motion of the source and the observer compared to each other. The V that appears here is the speed of the wave. So if we're talking about sound waves, then this would be probably 340 meters per second in the numerator and 340 meters per second in the denominator. If we were talking about light, it's the same equation, but it would be the speed of light in the numerator and the speed of light in the denominator. They don't just cancel algebraically, but a really important point that's in line with what you're saying is 340 meters per second is really fast. So unless these velocities, observer and source, unless those velocities are pretty big too, the change in the frequency is going to be very little. which is why you only notice the effect with race cars, because race cars are going very fast compared to the speed of sound. The speed of sound is about 340 meters per second. A race car goes, I don't know, 40 meters per second. So it's a significant fraction of the speed of sound, which is why you notice the effect. But you don't notice the effect of changes in frequency of my voice as I walk around the room, because my velocity is barely a meter per second, and the velocity of sound in air is 340 meters per second. We're going to have an opportunity later on to practice using this calculation, using this equation to perform a calculation. But for the moment, I just want to say that when the number is large, when the numerator of the equation is large, the frequency is larger. And so just based on that idea, that if the numerator is large, that makes the frequency higher, just based on that idea, I can choose how I'm going to use the signs in the equation based on my expectation of how sound waves behave. But I'm going to move on to my next topic without an example of this, but we will have an opportunity to calculate Doppler effects a little bit later on. I included this concept in today's discussion because I think it's one that doesn't really get covered well on this level of our education, this part of our educational journey, and then might get lost later on. It's the notion of sound level, describing how loud a sound is. It turns out that the intensity of a sound, how much energy sound has, because I had mentioned that as a wave, just like all waves, sound transfers energy through space. It's not the air that goes along, it's the energy of the wave. Well, Shidley, what do you mean, energy? What I mean is that there's a number that you can calculate that has the property that it never changes or changes predictably, blah, blah, blah. There's an equation that you can calculate for the energy of a wave. We're not going to engage that equation, but that equation depends on the square of the amplitude of the wave. It depends on the square of the amplitude of the wave. So when I make a loud sound, it's a sound wave with a large amplitude. It really compresses the air. And when I speak softly, which is hardly ever, it doesn't compress the air as much. And the energy in a sound wave is proportional to the square of that amplitude. We have a way of describing the loudness of sounds, which is called the sound level. It's a way that we describe how loud a sound is. A louder sound has more energy in it per second, and therefore has a greater intensity. I am not oblivious to the fact that that's the first time that I'm using the word intensity. What do I mean by intensity? Well, here are the units of intensity. Watts, which is a unit of power, which is energy over time, right? Like a light bulb has a wattage. Power. Per square meter. So it's not only the power, but it's also the area. So if I go up to a 60-watt light bulb and I hold up this piece of paper near the light bulb, the intensity of the light on the piece of paper is the wattage of the light bulb, 60 watts, divided by the square meters of the piece of paper. Watts per square meter. The human ear is really amazing. Human beings have the ability to hear very, very soft sounds, the scurry of a mouse, and yet we also have the tolerance to hear very loud sounds like the sound of a jet engine. In terms of power, those sounds are incredibly different from each other. The lowest sound that a human being can hear is about 10 to the minus 12 watts per meter squared. About 10 to the minus 12. That's a decimal point. You got to rock 12 zeros out there. And the loudest sound that we can tolerate, it's called the threshold of pain. It's a good name for a band. The threshold of pain is about 10 watts per meter squared. If your delicate eardrums inside of your ear get more than 10 watts per meter squared, not only will you be in pain, but physical damage occurs and you can lose your hearing as a result. 10 to the minus 12 all the way up to 10 is a massive span of intensity. So if I was to describe a loudness of a sound to you and say, oh, well, that was 10 to the minus 6, you have no idea what that means. It gives you no sense of what the sound is. Every once in a while in our science and in our everyday life, this happens where we want to describe a number that has a really big span to it. And when that happens, we use a log scale. The log scale that's used to describe the loudness of sound is called the decibel scale. So I have an equation for the sound level. The symbol that I use for sound level, haven't I recently really been going crazy with the lowercase Greek letters? That is the Greek letter beta, which I think is a little bit more familiar to folk. Beta is equal to 10 times the log of the ratio of the intensities. The reason why we use a logarithmic scale is the log makes it possible for us to compress the range of loudness of sounds to a more reasonable scale. In decibels, the lowest sound that you can hear, the lowest threshold of human hearing, it's the lowest value you can hear, is 0 decibels. The loudest sound you can hear at the threshold of pain, the sound before damage is happening to you, is 130 decibels. That's manageable. 0 to 130 is a manageable range instead of 10 to the minus 12th all the way up to 10. 0 to 130 decibels is a manageable range. Well, that's a very clever way of doing that. Yeah, not only do we do it with sound level, but we also do it with the Richter scale. The Richter scale that's used to describe the intensity of earthquakes, that too is a logarithmic scale. But nothing comes without a price. And so what you have to appreciate is that while it is true and quite obvious that a bigger decibel level means that the sound is louder, a 70 decibel sound is louder than a 30 decibel sound. That's easy. Very, very true. While that's true, the scale is logarithmic and not linear, and so the result is that if you increase the sound level by 10 decibels, that means the sound is now 10 times larger if you increase by 10 decibels. But if you increase by 20 decibels, that's not 20 times louder. That would be a linear scale. If you increase by 20 decibels, that means the sound is now 100 times louder. And 30, 1,000 times louder. I think you can see what's going on here. A 10 decibel sound and I get a 0. A 10 decibel change and I get a 0. A 20 decibel change, I get 2 zeros. A 30 decibel change, I get 3 zeros. And once you realize that pattern, it's easy to figure out the change in intensity of sound based on increasing by decibels. But it's a log scale. So a sound at 80 decibels is perfectly fine. And a sound at 70 decibels is perfectly fine. But that 10 decibel difference is a factor of 10 in loudness. The decibel scale as a indicator of sound level, which is related to sound intensity, the energy delivered by sound over time. You sometimes get a sense when I'm winding down, don't you? I want to take you by surprise all the time and go, "Ha-ta, I'm done." You go, "Oh, thank God." I was right, there was a lot of words in that, yeah. And there were some mistakes, and now I have to fix the audio to go along with it, and I have to fix that. So I am going to, there's not an exit for this yet, but there's an exit for yesterday's. And of course,